Happy birthday to
Yes, Torin, this is for you.
Happy birthday to you.
It is Halloween, by the way.
Happy birthday, dear Torin. Happy birthday to you. Happy birthday,
All right, here we go. I'm recording, Isaac. I'm on. Isaac, we're on. So, yes, you guys will go down as, after 30 some odd years of teaching, the most interesting class I've ever had, but that's probably a good thing, maybe. So anyway, topic. What we're going to do, topic today is we're going to talk about velocity. Velocity with parabolas. Okay, so write that down, velocity with parabolas, okay? So it's kind of weird. When you hear the word velocity, you want to think speed.
Yes.
Speed, velocity, and swimming. But speed and velocity are very closely related. Okay, so here's what we know. You guys know this formula. D equals RT. You know that.
No, we don't.
Yeah.
You do. Because if you were, listen, if you were to travel 60 miles per hour in your car for 3 hours, you would go a total of 180 miles, right? If you were to drive 60 miles an hour for 3 hours, you would go 180 miles, right? So it's distance equals rate times time, right? So rate is the same thing as speed, right? So that means if rate is the same thing as speed, then your rate is equal to your distance divided by your time. Okay, we're going to talk about that today. So velocity is speed. So for instance, if we wanted to find out how fast you guys swam across the pool, we'd get an average, right? Because we couldn't get, we could get a radar detector and get your instantaneous velocity, and we could know how fast. But technically, we'd say, yeah, we could get splits. And the thing about splits is it's still an average. Because you say, well, you went 100 meters in, give me 30 seconds or whatever. I don't know.
100 meters and 30 seconds.
Okay, so we'll make it easy. We'll say you went 100 meters in 60 seconds, right? So that would be a rate or a speed, right? That'd be a rate or a speed, okay? So we want to do the same thing. So first of all, to get there, we got to talk about displacement. So displacement is just saying how far did you go from point A to point B, okay? So displacement is just going to be distance 1 or distance 2 minus distance 1. Okay, real easy example. Okay, real example, you said splits, right? So let's say it is a 100-meter pool, but we got your split from 25 to 75 meters. We got that split, so the displacement would be 50. It's just distance 2 minus distance 1. So that's our displacement. How far did you go within that interval, okay? That's all a displacement is, okay? So then if you want velocity is going to be, okay, well, how fast did you go in that time? How fast did you go within that time? So you need your distance. So let's say you've got 50 meters, and let's say you did it in 5 seconds, okay? Then you can say how fast you went in 5 seconds. So say this is 50 meters, right? And let's say you did it in 5 seconds. Then your velocity is going to be 50 over 5, which is 10 meters per second, which is pretty impossible, but go along with you, okay? So that meters per second makes it like 10 meters per second, okay? Right? So it also looks like slope, doesn't it? Doesn't this look like slope? Turns out that velocity and slope mean the same thing. Velocity and slope mean the same thing. So anyway, I gave you a lot of information. Let's go into our example and see what we've got, okay? So example 1 says, using the table 1, determine the total distance traveled by the model rocket. So you shot up a model rocket, went up in the air, and it's coming back down, okay? Now one of the things we know is this. We do know. So you shoot up in the air, and it's going to start slowing down. When it gets to the very top of its path, for a moment, instant moment, it stops, and it starts to fall back again, okay? So its speed is going to slow down, slow down, slow down, slow down, and then it's going to speed up, speed up, speed up, speed up, right? So that means it should travel a lot of distance in the beginning, and near the end, at the top, it's not going to travel as much distance, and then come back down, okay? So, use data between 6 and 12. So let's find out where is 6 and where is 12. So I'm going to highlight that for us. I highlighter. Okay, so here's our 6, and here's our 12, right? So the question says distance, total distance traveled, okay? So that's easy. We're going to go 155.4 minus 192.9, right? So I'm going to go ahead and use my calculator to get that answer real quickly. Quit and clear. 155.4 subtract 192.9, and so yeah, it went negative 37.5. Okay, now that's feet, right? Or is that, no, that's meters. Okay, so now ask yourself an easy question. Wow, if it's negative, what does that mean?
It lost not much.
So it's coming down, right? Does that make sense? So it's heading up. So let's see if we can draw just a really rough graph, okay? So it's going up like a rocket, and what happened was probably we got a reading here and a reading here, okay? Got a reading here and a reading here. So for this part of it, it's probably going uphill, right? Right, so at a certain point, we are gaining it right about here. Right about here is probably at its top. You agree? You see that? Right about here it's at the top, 212 feet. And then it starts going down. So all of this positive amount here kind of got negated by the negative distance here, okay? Right? So we know darn well that the rocket did not really travel 37.5 meters. It didn't. It traveled a lot more than that because it went up a little bit, down a little bit more, and then down some more. Does that make sense? But overall, the average distance traveled from here to here turns out to be negative 37.5. Okay. Now that's not really good accuracy. It doesn't tell us much, right? Because we know by the picture, they gain some distance, right? Gain some height. They start losing height. But the difference between this and this turned out to be negative 37.5. Okay. So now let's keep moving on. What's the rocket's average speed? To get this average speed, we're going to have to take a look at our formula. Average velocity, speed and velocity. Okay, average velocity we're going to take then and do our negative 37.5 divided by 12 minus 6. Okay, and I'll let you think about it. Write that down. Because the formula says distance 2 minus distance 1, right? I got that. Over T2 minus T1, okay? And we get an answer of negative 37.5 over 6. Let me do that, divided by 6. And I get an answer of negative 6.25 meters per second, okay? Now, you guys are in physical science. I don't know if they've talked to you yet about speed and velocity, have they?
No.
Okay,
Yeah.
so a little bit. So here's the thing.
That one left.
A velocity, the only difference between speed and velocity, the only difference is velocity can be negative. Speed can never be negative. Speed is always positive. I mean, if you were to drive backwards from here to Kashmir, 60 miles an hour, that's still 60 miles an hour, right? You agree with that? So, but in physics, we'd say that since you're going backwards, we call that negative 60 miles an hour. So the only difference between velocity and speed is that velocity can be negative because velocity tells us a direction. Hold on. Hello? She is. I'll send her, okay? Landon? No, I'm just kidding. Alma? Mr. Hoyle wants to see it, okay? Yeah. So, so speed, you ready? Speed is always going to be the absolute value of your velocity. You guys have seen absolute value, haven't you, before?
No, a lot. We did it a ton in like 6 and 7.
Right, so it just says that absolute value just means whatever goes in always comes out positive. So if we want speed of this, we would just simply take absolute value of that 6.25 meters per second. Okay, so real quick, key
Per second.
no, because we haven't talked about acceleration yet, but hang on to that.
Wait, isn't it in negative?
Okay, now one more time. So
Oh,
if
never
if the question says, everybody listening? If the question says velocity, it can be negative. If the question says speed, it has to be positive. So again, here's how you remember it. You always remember it this way. Give your car drive backwards to catch it, okay? Okay, if you drive backwards, well, you'd get a ticket for one. You'd probably get in a wreck. But you could feasibly, on a carless night at 4 o'clock in the morning, you might be able to drive backwards on the freeway to catch it, right? But you're still going 60 miles an hour. In fact, on your speedometer, it will show 60, won't it, right? That's speed. But for velocity, we'd say, no, you're going negative 60 miles an hour because velocity shows direction.
Yeah, but you're still going to catch it.
Right. And so that's why we use velocity. We like to use velocity because we're saying, well, was the rocket going up or was the rocket coming down? Right? So at a certain point, Zoe, you know the rocket's going fast, but if you just look at the data and say, well, is it going up or down? So I look at this number and what do I know?
Going down.
Yeah, but that's a speed, isn't it?
Yeah.
That's a speed. That is a speed. But since it's negative, I'll say it's going down, so we use the term velocity. Because a lot of people say, no, you can't call it negative, because negative can't be a negative speed, right? But in physics and in science, we like to say, yeah, let's keep it negative, because then we know it's coming down. Okay, that's why we keep the negative, okay? So now, 3, let's make a scatter plot of this equation. Let's find an equation, okay? So let's do that real quickly. Let's take our time. Always put time on the horizontal. Time always goes on the horizontal, always. And we'll put our height here. Okay. So I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, right? I got to get all the way up to 200, so let's see. 1, 2, 3, 4, 5. Maybe I'll make that 100. 1, 2, 3, 4, 5. Maybe make that 200. So I'm going by 20s. That'll work for me. 120, 140, 180. Okay, and then 220. Okay, and 0, 0. 0, 0. I'm going to go 1. Of course, we have to estimate quite a bit because 7 is going to be right about there. 2 and 36. Maybe there. 4. I don't have any information on 3, but 4 goes all the way up to 134. 134. Maybe about there. 6. I don't have any information on 5 and 6. 192. About there. 8 and 212. It's about there, maybe. 10 is 192. Maybe there. 11 is 170. And 13 is 147. 147. There. 12 must be off. 12 is off. 12 is off. Get some white out here. I got a mistake. Good thing I have white out, huh? Oh, man. There we go. Alright. Where am I at? 14 and 141. Oh, that can't be right. I am definitely off. 13 is 147. 12 is 155. There we go. I think I'm getting it right now. 14. 15. You guys getting this done? $16 is 130. Okay, there's my scatter plot with a few little mistakes. Okay.
It's the coincidence that like time 6 and 10 are the exact same. that like always give the same type of thing?
You were asking a really good question. Will you hold on to that question? Please, honestly, I'm going to answer it, but I want to answer it later, okay? Because it's a really good question. Because there's something weird going on in this question that we want to talk about, okay? But I'm hoping somebody's going to come up with a brilliant idea, okay? So anyway, let's put these in the calculator, okay? So I'm going to go back to my stat, right? Edit, list 1, clear, list 2, clear, and I'll put in my data 0, 1, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, right? Go over list 2, 0, 7.4, 36.9, 134.2, 212.3, 192.9, 170.8, 155.4, 47.7, 141.9, 130.8. Okay, I got them in there. All right. Okay, and I'll wait for you guys. Okay, do you guys have the scatter plot done yet? Okay, and then you guys are getting it all in the calculator, okay? Oh, you did a much better job. I like yours better than mine. That's okay, we'll leave mine. Actually, I'm going to borrow yours. Yours looks better than mine. Thanks, Celeste. Celeste did a nicer job. She didn't make as many dumb mistakes as I did. Yours actually shows a really good picture of it. What's going on, okay?
Wow.
Okay. Okay, so it's a rocket. What do you think is going on? Anybody have any guesses?
It's just floating. It's a parachute.
Yes, yes, and yes. How'd you know that, Cody? Totally right.
Well, it's slowing down a lot.
Yeah, right. So, technically, can I rephrase that? It's not slowing down. It's still falling, but its rate at which it's falling is decreasing, right? We're saying the same kind of thing, right? Yeah. We're saying the same kind of thing, okay? So it has to have a parachute. You guys agree?
Yeah.
It has to have a parachute. So then, Aiden, let me answer your question. If it didn't have a parachute, absolutely, because it'd be symmetrical, right? We talked about the symmetrical. So that whatever time is here should have the same height
But
as whatever times are on the other side of it.
it would also
It just doesn't
burn,
deploy.
like all its fuel would be out when it's coming down.
How would it know
Right.
when to deploy the parachute?
Great question. So then my guess is, like most of these rockets, as soon as they tip over, the parachute gets deployed. A lot of them are that way. They've got their parachute on their nose. Remember, Lana, we used to have one of those cool rockets, right? We used to go up and then the thing would like turn over. As soon as it turned over, the cap would fall off, and then the parachute would just grab the thing, okay? Have you ever seen, you guys ever done that before?
Yeah, we did it in 5th grade, but they shot them all. They shot them like out so you couldn't get out.
They're kind of cool when you shoot them straight up because the parachute will deploy and they just come down slowly, right? So then the question is, where's the top? The top is probably here, right? That could be the top. So yeah, that was my next question. Nice job. I should be giving you the pin. So what do you think? Quadratic? Probably a quadratic. It looks like a parabola, doesn't it? So if I go to my, thanks Isaac, I agree, let's try quadratic. Okay, there we go. And I'm going to go L1, comma L2, right? Mismatch. Why mismatch? Go to. What did we do wrong? All right. Yeah, I got the problem now, huh? Celeste, let's see what I did wrong. Stat, edit. Oh.
What is that calculator?
Oh, no. I missed a number.
I got y equals negative
Can I use yours?
20.
I missed a number.
It's
Okay.
L1, L2, right?
Yeah. So, Isaac, nice job, Isaac. So did you guys get this answer?
No.
That's a 42, but it's hard to see the 42.
Yes, I did. Yeah.
So our quadratic should be y equals a negative 2.2x squared plus 42.7x minus 14.3, okay? Now,
Oh.
Easy to do.
Did he get ABC?
Oh, let me keep. Can I keep talking? Okay. All right. So we took the ABC, right? Took the ABC and plugged it in. Am I going too fast? I'm going to slow down for a second. I just. Oh, sorry. So there's Isaac's numbers, and I just put it in equation, okay? Yeah. How's that? Is that better?
Yeah.
And that is a 42. It's the calculus got a smudge in it. Okay. Okay. Now, you're right, really. I'm going to show you one more thing. You don't have to know this, but I want to show you something today. Okay. I want to show you a scatter plot. So I'm going to go to my scatter plot. It's on. Okay. Good. My scatter plot's on. I'm going to go to my window. I'm going from 0 to 16. Just want you don't just watch, okay? We're going to learn this later. From 0 to about 220. Okay. All right. Graph. Okay, there it is on my calculator. Can you see the scatter plot on my calculator?
Yeah.
Did you guys ever do this in Mr. Bard's? Probably not, right? So your calculator can also do the scatter plot, okay? But I had to make the window fit the window of Celeste's graph, right? And now the next thing I want to do is put my equation in and see how well it fits. So y equals negative 2.2 x squared plus 42.7x minus 14.3. And again, you don't need to know this yet. I'm going to teach how to do this later. I just want you to see it, okay? So what I'm going to try and do now is, I've got my scatter plot. I want to graph my line on my scatter plot and just see how the two match up, okay? So let me hit graph, and we'll see how this works. Graph, okay? All right, so our quadratic did a pretty good job of fitting most of them, didn't it? But it didn't fit all of them. So what we could say is that it's probably accurate from here to here until the parachute got deployed. You guys agree with that? And once the parachute got deployed, it was no longer a quadratic. This curve right here is not a quadratic at all. Now there is another one that it might look like. What about a cubic? Remember how we did a cubic? Cubic. All right, hold on. So if I go to my stat, calculate.
You just passed a cubic.
Oh, I did it. There's my cubic reg. Thanks, Isaac. L1, comma L2. I just want you to watch. You don't need to do this. I'm going to write this equation down. So I'm going to have a y equals a 0.113x squared minus a 4.9, oops, cubed. 4.9x squared plus a 60x minus a 30.6. Let me put that in my y equals. And again, I'm just showing you stuff right now that we will learn later, but I want you to see this, okay? So 0.113x to the third minus 4.9x squared plus 60x minus 30.6. Let me graph that. Hey, that's a better fit. Can you see it? Can you see that? That's a better fit, isn't it? All right, so what am I doing? I'm slowly throwing at you, because it's the way I teach. So I'm just showing you other ideas, because eventually we're going to talk about cubic equations, right? We've talked about it once in your last test. I showed you a cubic now, because some patterns need a different equation to fit it better, right? We looked at a power equation yesterday, didn't we, right? So what we're going to do eventually is find the best equation to fit the best data, okay? All right, how are we doing? All right, turn it over. Let's see what we got. All right, factoring. Let's see if you guys can factor these real quick. And I'm going to stop the recording, okay?